computer. So this will be uploaded probably half an hour after we finish. Okay, so now we've got f of x equals 2 to the x plus 4 sinh of x. And the thing is that I can just go inside of my book. I can go in and take a look at the table on 352. Okay, the first one, 2 to the x. Okay, right? If we remember, if I have, let's say, for example, I have big f of x equals 2 to the x. All right, then when I take f prime of x, or big F prime of x, that's going to end up equaling 2 to the x natural log of 2. So the 2 to the x remains the same, and we multiply by the natural log of 2. So what that means from an antiderivative standpoint is we're going to keep the 2 to the x the same, but we're now going to divide by the natural log of 2. Okay, so my big f of x, my antiderivative, is going to equal 2 to the x now divided by the natural log of 2. Then plus, and this is, we look at sinh x is just cosh x. So if you look on the table, this will be plus 4 cosh x. And that's it. This one, I have an expectation that you know. This one I do not. Plus C. Thank you for plus C. Always. See, details. Details matter. All right. Any other questions on the homework? $63, he says. All right. Oh, we skipped. Oh, wait. Yeah, we skipped. Is that 4? Oh, that's chapter 4 review. That's not the one I want. I want 63. Okay. We have, and that's a great question. This is about acceleration. Oop. So our statement here is 63. Here is a of t is going to equal 10 sine t plus 3 cosine t. Okay. S of 0 equals 0. S of 2 pi is going to thus equal 12. Okay. And so what we have here is we need to find the position function. Find S of t, the position function. Yep. Okay, great. So what we're going to do is we're going to find two antiderivatives. Okay. And so we start out and we'll say, all right, so we'll find first v of t, which is the antiderivative of a of t. Okay. And so we have 10. And then the antiderivative of sine t is going to be negative cosine t. So it's negative 10 cosine t plus, and this will be 3, and the antiderivative of cosine t is 3 sine t. Then plus a c1, okay? Because that is now our first derivative, that, or the first antiderivative that we have to take. Now to find s of t, we're going to take the antiderivative of negative 10 cosine t. So that's going to be giving me negative 10 sine t. Minus, right, because it's now going to be minus 3 cosine t, because the antiderivative of sine t is negative cosine t, plus c1t plus c2. All right. So Bill, did you get that far? All right, cool. So was it a matter of just like plugging in the points now? Good. Good. Well, let's finish this up because we should. We've now got 2 points here, and what we're going to use is we're going to use s of t. So s of 0, okay, is going to equal 0. So that's negative 10 sine 0 minus 3 cosine of 0 plus c1 times 0 plus c2, and we see that that's equal to 0. Okay, so this is now equal to negative 3, right? Because sine of 0 is 0. Negative 3 cosine 0 is Cosine 0 is 1, okay? And then there's a 0, so it's -3 plus C2 equals 0. And so that gives me C2 equals 3. All right? Now I can use that information in order to plug it back into my equation. By the way, on your exams, some of you need to work on just some basic Unix circle stuff, right? I got this. If I have sine of pi over 2 times 2, this is equal to the sine of pi, right? Because they cancel. And sine of pi is equal to 0. That was on your mean value theorem problem. A lot of people miss that. And so you probably want to make sure that you know, so at least your basics on the unit circle, right? Your basic values on the unit circle. All right, so now we're going to put in C2 into our function. So now S of 2 pi is going to equal -10 times sine of 2 pi minus 3 times cosine of 2 pi, okay, plus C1 times 2 pi plus 3, and we're going to say that that's going to equal 12. So that's our second equation. And sometimes you might have to use a system of equations in order to do these things. So another one of those things that you probably want to make sure that you feel kind of comfortable with. And so this is now -10 times 0. So this is 0 minus 3 times 1, so that's -3, plus 2 pi C1 plus 3 equals 12. So that gives me that 2 pi C1 equals 12, because the -3s are going to go away. The -3 and 3 will go away. So C1 equals 12 over 2 pi, which is equal to 6 over pi. Okay, just a little algebra there, and trig, obviously. So S of t is now going to equal -10 sine t minus 3 cosine t plus 6 over pi t plus 3. And that is my position function. Any questions? All right. Okay. Folks, here's the deal. Get 4.9 done tonight, okay? It's going to come in extremely handy, right? Just practicing your antiderivatives, because legitimately tomorrow we're going to do the definite integral, right? Okay. And when we do the definite integral, you're going to use the antiderivatives. So get some practice. Get some practice tonight. All right. Don't fall behind. I have to say that on our last, as I was looking through the grades and the like, and I was looking at, there were a sizable group of you who didn't turn in your homework for 4.1 through 4.8. Okay. And, you know, and it's become a little bit of a pattern also for chapter 3. There were some people who hadn't turned in that in either. I don't know how it is that you're going to do well in calculus without actually doing the homework. It's so absolutely necessary. So you got to get in there. You got to do it. You got to do it before we actually do our exams, that sort of thing. Okay. All right. And we've only got like a week and a half left. So yeah, there you go. Okay. So I just wanted to let you know, clue you in. That's what's going on. So let's go in. What we're going to do today, it's going to be a little bit more lecture based. Okay. It'll be a little bit more lecture based, but that should be okay. You will have an opportunity to kind of work through some things. I'm going to kind of go slowly. The concept actually itself is not all that bad, I don't think. I think the problem is in the notation and how the notation gets used. So we're going to spend some time with the notation, getting kind of used to it, learning how to read it, learning to figure out what it means, okay? Because the notation can get a little hairy. But the ideas and concepts, not bad at all, I think, right? It's just a matter of like drawing rectangles and counting rectangles, Okay, and so that's what we're going to do today. We're going to do now 5.1. We're going to start talking about areas and distances. All right, so we're in the notes now. So what we're going to look at today is we're going to be looking at areas and distances. And when we talk about areas and distances, we want to talk first about how do we calculate area, okay? And the simplest way to calculate an area, for example, with a square like this, right? We'd use our length times our width, yes? With a trapezoid, we've got a formula. The formula is basically our base times our height, right? That actually is the area of the figure, is base times height. Triangle, right? We'll use base times height divided by 2. And with a trapezoid, we'll take, half of the base plus half of the other base, right? And we'll divide that through by 2 as well, okay? So in general, when we calculate area, what we're going to do is we're going to calculate, and so like you don't have to have those memorized right now, although you probably do. When we calculate area, right, we generally have these formulas. But what about a shape like this, okay? What about a shape that looks like this? Well, that is a different problem, okay? It's a different problem, and that a lot of it, sometimes we might do things like, oh, okay, well, I might, draw a rectangle here that captures that piece, and then I'll draw another one here that captures this piece. But what about like when I hit this curve? What do I do with the curve, right? Do I go under the curve? Do I go over the curve? How do I break it up into pieces, right? And so basically we have this problem, okay? And the problem of integral calculus is how to calculate area. That's the problem of integral calculus, okay? So what I'm going to do first, all right, I'm going to move away from this because I'm going to need a bigger sheet of paper, okay? That's basically what's going to happen. So we're going to do this first question. Estimate the area of f of x equals the square root of x, okay? From 0 to 4. So I'll take my little snipping tool. All right. I'm going to go into a different page. Okay, so we could get a little bit more space here because we're going to need a little bit more space than we have right now. All right. So now we're going to estimate the area under the graph of f of x equals square root of x from x equals 0 to x equals 4 using 4 approximating rectangles and right endpoints. Then we'll sketch the graph and the rectangles. All right. And then we want to determine, is my estimate going to be an underestimate or an overestimate? Okay. So I'll start out and I'm going to sketch the graph. So that's the square root of x. That's what it looks like. And we'll have this be 0, and this will be 4. Okay. And we want 4 approximating rectangles and right endpoints. All right. So what we're going to do is we're going to break this up into 4 pieces. So we'll go 0, 1, 2, 3, and 4. Okay. And what we're saying is we're going to use approximating rectangles. And so an approximating rectangle means that we're going to start here. We're going to start on the right-hand side. So we'll start at 1. That's on the right-hand side of the box. And I'm going to construct a rectangle. Okay, I'm going to construct a rectangle at 1. Then I'll go to 2 because that's now going to be the right-hand side of the next box. And I'm going to construct another rectangle. Its height is going to go up to the curve at 2. Then I'll go to 3. All right. And I'll construct another box. And then I'll go to 4. I'm going to construct another box. So those are my rectangles, 1, 2, 3, and 4. Okay. We used a right endpoint. So this is the right-hand side. And that's just something you want to notice. Right, right, and right. So when we say something is a right endpoint, okay, or using right endpoints, what we're doing is we're doing the ones that are further along the line. So we've broken up our graph into 4 pieces, right? 4 approximating rectangles. And we pick the right-hand side, okay, in order to draw the heights of those rectangles. Okay. So now what we need to do is we need to find the area of each one of these. So the value, the width here, which we're going to call delta x equals 1. Okay, so delta x equals 1 because that's the actual width there. And so 1 to 2, that's going to be 1. 2 to 3 is 1. 3 to 4, that's 1. So all the widths are the same size. Now what we need to do is we need to find their heights. And to find their heights, what we're going to use is we're going to use f of, in this case, f of x. This will be f of 1. This one here is going to be f of 2. This will be f of 3. And this will now be f of 4. Okay? So the height of the area of the first rectangle is going to be the f of 1 times this delta x. Okay, f of 1 times delta x. And so we'll calculate f of 1 in just a moment. All right, plus f of 2 times delta x. That's the second rectangle, so this one right here, plus f of 3 times delta x, plus f of 4 times delta x. All right, so notice that in each case, what we have is delta x is going to remain the same. Delta x is always equal to 1, all right, because we use the same length for each and every one of them. But what changes is going to be our height, and our height is based upon our function f of x. So do you have any questions about that? Okay. All right. So to make this estimate, what we're going to do is we're going to take, well, first f of 1. So this is going to be the square root of 1 times 1. Excuse me, the square root of 1 times 1. Plus f of 2 is the square root of 2 times 1. Plus the square root of 3 times 1. Plus the square root of 4 times 1. And that ends up equaling, right? If you go in, you do a little bit of calculation, pop out your calculators, okay? We end up equaling 6.1462. Six three actually, if we round. So take a check, see if you actually got the same thing. Okay. All right, great. Now the trick here is just, do we understand the process that was used in order to find, I caught that, that's funny. Do we understand the process that's used in order to actually generate these rectangles, right? Because that's actually going to be the big concept that we've got here, okay? Now, look at this. Let's take a look at it, all right? And tell me, do you think that this is going to overestimate the area? Okay, will this overestimate or underestimate the area? And why? Everybody was quick to it. They're like, yep, totally get it. Why does it look that way? Well, the rectangles are bigger than our curve. Yeah, it's got extra space. That's exactly it, Phoebe. It's got extra space, okay? There are spots in the rectangle that aren't part of the actual shape. The entire shape is actually covered, right? Okay. Yeah, exactly. So it's an overestimate. And the only way that we can get whether or not something's an overestimate or an underestimate is to actually draw the figure generally. Okay. There are some times when you have a really good sense of the figure, when you can figure out if it's an over and under, but not always. Okay. So we got to be a little bit careful with that. Generally, yeah, Mina asked, do we subtract the overestimate from the right? Not exactly. We're actually going to get even trickier here to actually figure out what the actual area is. Okay. It would be an underestimate. That's right, Rashi. There would be an underestimate here if we actually were using the left-hand side. We're going to see that in just a second. Okay. Because, yeah, can we make a bunch of rectangles? You absolutely could. We're going to get to that too. Right. Guys are sharp. Love it. All right, so let's take a look at that left endpoints one. All right, so we're going to use the left endpoint one. I'm going to draw another graph. Okay. And we're going to do the same function, right? We're going to go out to 4. Okay. And I've got 1, 2, 3, 4. Okay. What if we use left endpoints? So this is the second one. I'm just writing it out rather than using the next font. What if we use the left endpoints? Okay. Well, let's take a look. Okay. So go ahead, try it out, right? So now we start here, we're gonna start at f of 0 for the left endpoints, okay? And then next one, we'll go up to 1, but that means that this thing, that's gonna be our graph there, okay? Right, because we're using the left endpoint. Then we can go up to 2, and that's the left endpoint of the next rectangle. And then we go up to 3, and that's the next endpoint of that rectangle, okay? What is delta x? So delta x is what in this case? Yeah, exactly. It's going to end up being 1. That's right. Delta x equals 1. Okay. And let's go out and take a second to write out the function. So we want to now find the area. So the area for these 4 boxes is going to equal, if we write it in terms of our function, it's going to be f of 0 times 1, or times delta x, right? Because here's delta f of 0. And then this will be f of 1. This will be f of 2. This will be f of 3, and we're not going to use f of 4 now. So we started at 0 because that was our left-hand most endpoint, right? And then we went up through 3, okay, because 4 is not a left endpoint, or f of 4 is not a left endpoint. So it's not going to be included. So that's different. So we'll have f of 0 times delta x plus f of 1 times delta x plus f of 2 times delta x plus f of 3 times delta x. And so once again, we're just going to plug in f of x. We're going to plug in these values for f of x, excuse me. So this is going to end up being 0 times 1 plus 1 times 1 plus square root of 2 times 1 plus the square root of 3 times 1, okay? And that ends up equaling 2 less than the last time, right? 4.1463. Approximately, obviously. So that's a left endpoint, all right? So when we're drawing the areas, we like have some choices as to how we're going to actually draw our boxes. Now, in this case, underestimate or overestimate? Yeah, this is an underestimate because all of our boxes are under the graph. Okay, underestimate. So all of the boxes are underneath the graph. Okay, makes you all feel warm and cuddly inside. There you are. Good. Yes, you could. Yeah, you could choose any shape that you wanted to, Misha. It's not really, no. It turns out it's not. And the method that we're going to use in order to find our integrals, we're going to use rectangles. Right? And it's going to turn out it's going to be very nice. Yeah. You can use any shape you want, really. You could like, hey, can't we just put a bunch of circles in here? And that would be harder. It would be much harder. But you could do that. That would be an option. Okay. Now, what if we used midpoints? Okay. Let's take a look at another one here and let's ask, what if we used midpoints in order to draw this out? What about midpoints? Go in and draw our picture again. You know what? I'm going to give myself a little bit more room on the bottom. There we go. Here's 2. Oh, not 2, 4. Here's 0. And now we'll go 1, 2, 3, and 4. We're going to draw 4 triangles, okay? But now we're going to use the midpoint between 0 and 1, okay? So we've got a midpoint between 0 and 1, and so that's at 0.5. So our height is going to be f of 0.5. That's going to be the height of the rectangle. The height of the second rectangle, that's going to be f of 1.5. Third rectangle is going to be f of 2.5. The fourth rectangle is going to be f of 3.5. That's my third rectangle, right? So when I look at my areas, if we notice, what we want to notice is that we still have, okay, we still have our delta x is going to equal 1, right? Delta x equals 1. That's the length, okay, because I took the entire length of the entire thing and I divided it by 4. So it's still delta x equals 1, but we're just going to calculate our areas, okay, utilizing the midpoint. So this will be f of, our area will equal f of 0.5 times delta x plus f of 1.5 times delta x plus f of 2.5 times delta x plus f of 3.5 times delta x. Okay, and that'll then equal, right, root 0.5 times 1 plus root 1.5 times 1 plus root 2.5 times 1 plus root 3.5 times 1. And that's going to approximately be 5.3838. Okay. Is this an overestimate or an underestimate? All right, Valet, you're saying that it's an overestimate, but it does look closer. Why do you say that? You can unmute.
Well, just from the picture itself, it looks like the excess is not as big as the first one.
Okay.
But the
All
picture,
right.
I know pictures not drawn to scale all the time. I understand that, but it looks like it's closer.
Well, yeah, I totally get that. And if you actually think about it with the way that, if you think about how square root function goes, the square root function, right, it increases, derivative, its slope gets smaller and smaller, right? So we'd expect that this part right here is actually going to be bigger than this part right in there, okay? That part, the part that's overlapping is bigger than the part that's underlap, right?
Right. Mm-hmm.
I mean, and that just has to do with the function. If you kind of look at it, you're like, oh, okay, that's true. And right, and that's because that slope kind of decreases, right? Or yeah, the slope decreases, and so hence the pieces get smaller and smaller. Like that's a really big piece right there down near 1, right? And then we get a smaller piece here, okay? And then we got a fairly big piece, then smaller, right? So each one of the underestimated pieces, okay, is smaller than the overestimated piece. So hence, it looks like an overestimate. And it turns out it is. It is an overestimate. Is it a better estimate, though? But is it better? Is it better, say, for example, than either the left or the right? Does it look like we have the actual amount better than we did before?
Yes.
Yeah. Okay, why do you say that, Ville?
Well, because it has both the over and the underestimate, so it kind of counteracts the sway of the gap between the actual value and your overestimate.
Yeah, I mean, one of the ways that we can kind of look at this, that's exactly it. It kind of counteracts, is we could imagine moving this piece into there, right? Moving this piece into there, right? Okay. Moving that piece into there, okay, to where, it's like, oh, it kind of fills up. It fills up a little bit more than we need, but it's not anywhere near as much as we had when we had the right endpoint one, right? I mean, like the right endpoint one was way bigger, okay? So, but is it better? And the answer is yes, right? It's a better estimate. So the midpoint one can actually give us a much better estimate than both the left and the right. And oftentimes that's going to be the case. Most of the time, the midpoint area is going to be a better estimate than the left or the right. Okay. So this starts us out with understanding the basic concept behind finding these areas and what will eventually become what's called our Riemann sum. So our Riemann sum is basically going to be this process, right? The process of finding ever more areas of rectangles underneath a curve. Okay, and so we'll often talk about that. What's the size of the rectangle under the curve? This is the idea that we're working with. These are the rectangles under the curve. All right, let's take a short break. Let's go to 1150 actually. All right, so we're back in. So how is it that we're going to make each of these estimates more accurate? Okay, and so we're going to look at this, and this is going to become a big piece of this. Is we can increase the number of rectangles. So if we increase the number of rectangles, then what we do is we shed off more and more of the inaccurate parts, right? There's going to be less and less of that error places. Okay, so we can increase the number of rectangles to either fill in gaps in the case of an underestimate, or to cut off excess. Right? So you can either cut off the excess pieces by adding more rectangles in, or you can fill in the gaps by adding in more rectangles, right? So if we make the size, right, basically this is saying make delta x smaller. So we're going to make delta x smaller, right? You just make smaller and smaller and smaller subintervals. And if we think ahead a little bit, remember delta x, we got another name for delta x, if you remember, okay? This is from 3.10, which a lot of you still need to do. This was dx. So delta x is dx, right? Delta x is this piece that's the change in x, which also ends up getting called dx. Okay. So that's interesting, right? Because there's a connection here that's being made to the derivative. So as we make delta x smaller, okay, we get this dx piece, right? That whole idea of, right, getting smaller and smaller and smaller subintervals, okay, right, until we get an entirely accurate picture of this area. All right, so we're going to get into a bit more when we hit 5.2. Now, so let's take a look here, and let's look at this. The area A of a region S that lies under the graphs of a continuous function f is the limit of the sum of the areas of approximating rectangles. Okay, So basically what happened, right? Okay, we did this. We went in and we took areas, and we had 4 areas that we did originally, right? So we had, say, for example, we did f of, we'll call it x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x. Okay, right? And that's what we did because we had 4 subintervals. But we can actually imagine that what if we wanted to take 8 subintervals? What if we wanted to take 15 subintervals, right? Or 20 subintervals? Much, much bigger amounts of subintervals. Well, in this case, what if we wanted an infinite number of subintervals? N, right? N is the number of subintervals. Okay. Right? So n is the number of subintervals. And what we're seeing here is that the area under this curve, right? Under the graphs of a continuous function f, right? The area of it is going to be these, all of these areas, the individual rectangles, as we make the number of rectangles that we draw really, really big, okay? Right? So as we make them really, really large, right? And so you can kind of see the picture here is to, give you a sense of what happens if you increase the number of rectangles, okay? And we can kind of imagine too that if we wanted to make this a better approximation, okay, we'd actually, like you can imagine doing something like this, right? Here's that. So now I've added in this piece into my approximation, okay? And then over here, okay, I would, got that piece. And so now I'd add in this piece right here. And so this is now the new rectangle, okay? And so I add in that little piece. So I've actually added in more of my rectangle. Or I add in now here, okay? So this one actually ends up being pretty much the same, right? They don't always change, okay? But I add in another rectangle here. And what I do when I add in this rectangle is I actually shave off this piece right here, the overestimate. And if I add it in this rectangle, I make my overestimate smaller by adding in a new rectangle, okay? By cutting it up into 2 sub pieces, okay? If I take this one here, this now shaves off all of that area. That overestimate ends up getting taken out, right? Because now my new rectangle looks like this, okay? So you can see as you add in more rectangles, what you're going to end up getting is a better and better and better estimate. And hence why the limit as n approaches infinity, right, of Rn, okay, is saying as we make an infinite number of basically these rectangles. So as we make the number of rectangles that we have, we're going to get better and better estimates, right? Because we're going to shave off excess pieces and we're going to add in pieces that we've been underestimating. It's a deep concept. You're going to have to spend some time thinking about it. Okay? We would. Yeah, Misha, we're going to get to that in just a little bit. We would. What would end up happening? So what Misha is saying is, and this is a very interesting point, is that if you make these really small rectangles, if you make delta x, right? If you make delta x very small, right? Very small, then what you get is you essentially get what looks like a line, all right? You get what looks like a line, all right? And you might ask yourself, well, lines don't have areas because it has no width. Well, that's the magic of calculus, Misha. What we will find is actually that we can actually accumulate all of those little lines. We're going to accumulate them over and over and over again. Take an infinite number of them, and by taking an infinite number of them, we're going to fill in the entirety of the graph, okay? We're going to fill in the entirety of the area under the graph, and we are going to get the actual area, okay? We would get a line because we'd have no width, right? Very small delta x, okay? But it would give us our actual area. right? And we'll get a picture of that in just a minute. Okay. So the definition and the picture above are for right endpoints, but the same can be said for rectangles forming using left endpoints. So we can also use left endpoints. In fact, we could take the height of the ith rectangle to be, and ith rectangle means like this rectangle right here that starts at xi. So this is f of xi and xi. So this is the ith rectangle. It's just a generalization. So when I say the ith rectangle, it's pick any one. The second rectangle, the third rectangle, the fifth rectangle. We'll choose one in general. That's what we mean by the ith rectangle. Okay. So we can take the height of the ith rectangle to be any value of f at any number xi. So any number, any value on the x-axis. Okay. In the what we call the ith subinterval, right? So again, just to help you out, this is the first subinterval, x1 to x2, that's the second subinterval, x2 to x3, that's the third, x3 to x4, that's 4, then 5, 6, 7, right? That's the idea of the ith subinterval. We just use that there to, we use the I, okay? So the I gets used so that we don't have to use we don't have to define something. We don't have to use a specific number. We don't have to say the 1, 2, 3, 4, 5, 6, 7, like choose a number. We just say it's the ith subinterval, and that allows us to say that we can pick any interval, right? Any interval, and they all end up having the same characteristic, okay? So we call the numbers x1, x2, xn the sample points, okay? And so if you look at this picture down here, where we're using now the left endpoints, okay? Or rather, excuse me, the sample endpoints. So now we're going to use x1. So, pardon me, we'll choose anything in here. So anything in the interval, like an x1 now, okay, or x2 is now chosen here, okay, as being a different point within that interval. x3 is another point within that interval, okay. And what you'll notice is that these x1s, they're not at the same point. Whereas, or excuse me, x1 star. x1 star is not at the same point as x1, okay? x2 star, right, and those are actually our sample points, pardon me, I misspoke. They're the places where we say, okay, well, I'm just gonna draw in these points because they're gonna actually give me the best estimate, all right? I'll pick ones in which we get the best estimate. And so I'll give you a sense of some that we can choose, right? So the endpoints or the values for f of xi that we have for these areas, they can be chosen any way that we want to, okay? We can choose them any way that we want to. And so in this case, right, we're just going to make an arbitrary choice of our xn's. Our delta x remains exactly the same, okay? It's just going to be a minus b divided by however many we have, okay? And that's going to end up giving us our area. So the whole point of these two illustrations is to show that we can choose where to sample, right? Where to draw our f of xi's anywhere we want, right? So this is f of xi x1 star, okay? And then I chose this new one here, and this gives me f of x2 star. So they can be chosen anywhere we want in order to generate these areas. Any questions on that? All right. Yeah. Actually, this area function is not for the left endpoints, Misha. Notice that we didn't choose left endpoints. We specifically chose wherever we wanted. Okay. The first one was right endpoints. Okay. Or I think the first one was right endpoints. Yep. Or yeah, right endpoints. This one actually, notice that x1 star is not at the right-hand side or the left-hand side. And x2 star is in the middle. It may not be exactly the middle. It doesn't matter. And x3 star, okay, is actually at neither the left-hand side or the right-hand side. So these are sample points where we get to choose any one that we want based upon what we think will generate the best estimate. I know. For those of you who are like, wait, but how do I choose? And the answer is whatever one makes the best estimate. Okay? right? It's a little bit, it's less process driven than that right endpoint and left endpoint. Okay, now we're trying to get our best estimate. No, that's not true, Misha. So Misha asked, is it the same distance from x1 to x3 as x2 to x3? That's not true. Okay. These distances now, they're different. Okay. All we need is that x1 star is in the first interval. x2 star is in the second interval. x3 star is in the third interval. So we just need that they're actually in these intervals. The intervals remain exactly the same length, okay? And they have nothing to do with the sample points. The sample points have to do with our y's, right? This y1, this y2. Okay? Yeah. So they're just, we just pick them for inside of the interval, okay? And then they tell us, right? They just tell us where to pick our y's. They show us where our y's are. The intervals, the delta x's, remain the same. Just like with the midpoint ones. No. Well, the distance from x1 to x2. So x2, so Bill asked, is x1 equal to x2, x equal to x3? No. x2 minus x1 equals x3 minus x2. So those distances are true. And notice no stars. No stars. So those are the subintervals. They are the same distance. Deep, deep stuff. Right? But the whole idea here is we can generate these rectangles. Okay, we're going to be able to generate these rectangles. All right. Now, let's talk about upper and lower sums, because allowing that we could sample from anywhere allows us to generate upper and lower sums. Okay? So an upper sum is formed by choosing points xi so that f of xi is the maximum value of f on the ith subinterval. Okay? So basically the idea now, so like this would be the first subinterval. Okay? The maximum value on the first subinterval is right up here. Okay? And so we choose that as our max. And so that would be the upper sum for that rectangle. Down here, that's the lowest value on that subinterval. Okay, so we generate a square utilizing the lowest value, and that's the lower sum. But we do that for every single one. So the dark blue ones are going to end up being our lower sums, and our light blue ones are going to be our upper sums. Because you can see, like down here, that's the lowest value on the second subinterval. So we'll use that as the lowest value or for our lower sum. And this up here, that's the biggest value. So we'll use that one as our upper sum. Okay. Same thing here. This is the lower sum. This one up here is going to end up being the upper sum. And so notice, right, that the difference here for the first subinterval, okay, the upper sum ended up being the left endpoint. Okay. But for the third subinterval, the upper sum ended up being the right endpoint. So it just depends upon where the function is largest on that interval. So where is the biggest value for the function on the interval? Okay, and that basically is the distinction between an upper sum and a lower sum. Okay, it's going to change our heights. Delta x remains the same. In fact, delta x is always going to remain the same. Okay, the change is in how we pick our x's for y equals f of x. So when we want to find basically our y values to give our heights, right? Our heights for each rectangle. Any questions on that? All right. So now let's take a look at some sigma, what's called sigma notation. Okay. So sigma notation is basically summation notation. Gotcha. Yeah. Well, this is integrals because we are going to be taking sums. but it'll be okay. I think hopefully we'll get this. And in fact, no more than hopefully, I know you're going to get this, Misha. It'll be fine. So now we look at this and we see here's the sum, and then we say that the sum of the area, okay, is going to equal, we just add up f of x1 times delta x plus f of x2 times delta x plus f of xn times delta x, okay? How we write that then is we write it this way, okay? We have I equals 1, so that starts with our 1, and we go to n, and the n is the last term, and then what we're going to do is we're going to take f of xi, and that's where that ith term comes in. So I will be 1 for the first one, and then we'll do it for the second one, then the third one, all the way down to the nth one, right? We'll do it from 1 to n, okay? And each time we're going to be multiplying by delta x, then we add them all together, okay? And that's our sum, okay? So these two things, these are equal, right? They're equivalent. And that's what that summation notation means, okay? And now what happens is we can utilize that summation notation in order to give us the area, okay? To give us the area when we actually make our rectangles very, very small. So A here is going to equal the limit as n approaches infinity, okay? So like as we make the intervals very, very small, okay? So n is the number of intervals. As we make those intervals very small, we're going to actually just do the same thing. We'll take f of xi times delta x, okay? We're going to do a lot more of this in 5.2, right? In our next section. All right. So what this means here is that's the add up all of the terms from 1 to n. Okay. So let's actually try it out a little bit. We're going to try it out with a problem. And yeah, so we'll try it out with a problem. Why don't we take a 5-minute break and then we'll get together for that problem. All right, so now let's take a look at evaluating the upper and lower sums for f of x equals 1 plus x squared, all right? And we're going to get this interval. It's going to be from -1 to 1 with n equal to 4, okay? And so what I want to do here is I'm gonna write this up utilizing the summation notation, okay? And so this is going to be the sum of I equal 1 up to 4. Okay, so n is going to equal 4. I equals 1 up to 4. And we'll call it f of xi, okay, times delta x. Okay, now our delta x, in this case, delta x is going to end up equaling, it's going to be the endpoints. Okay, so we'll call this one a, and this will be b. Okay, so this is going to end up being b minus a divided by n. Okay, so that's going to be our delta x. And I'll draw you a picture of it to just show you that. And so that's going to be 1 minus -1 over 4, which equals, right, 2 over 4, which equals 1/2. And that's going to end up being my delta x. Okay, so that's going to be 1/2 is going to be delta x. And my f of xi, we're going to get into this in a little bit. My f of xi is going to change for each one of my values. Okay, and so what we'll do is we'll first draw a picture of this to determine what my f of xi is going to be if, say, for example, we use an upper sum. Okay. That is the highest value, the biggest value, the maximum. All right. Now, think to yourselves, because you just took an exam of it on it, if you have an interval, how do you find the maximum on that interval? Right? It's a 3-step process. Yes? Right? We find the critical numbers. Yeah, we take the derivative, find the critical numbers, and then we find the values at its endpoints. Yes? Exactly. Okay? Now, what we're going to do is we're going to find the critical numbers for f of x equals 1 plus x squared. So we'll first find our critical numbers. Okay? And what we'll get now is we're going to get f prime of x is going to equal 1 plus x, not 1, is going to equal 2x, okay? And then we'll set that equal to 0. So 2x equals 0. So we're going to have a critical number at x equals 0. So everywhere else on this graph, okay, everywhere else on this graph, it's either going to be our right-hand endpoint or our left-hand endpoint, because inside of any one of the other intervals, there's not going to be any any critical numbers, only at 0. Okay. Now, I should actually change this up a little bit, make it right in the middle. Okay. Now 1 plus x squared is going to be right here. So here's 1 plus x squared, better known as x squared plus 1, which looks like that. Okay. And now we're going to start at, we'll make this -1. Here's 1. So those are n values. Okay. And I'm going to have each one of my delta x's is going to be 1/2. So I'm going to go from -1/2 to -1 to -1/2. Okay. Then at 0, then I'm going to go to 1/2 and then 1, making each one of my intervals all the same size. Draw that a little bit better. There you go. Okay. Once you've gotten that, let's go in and draw in the lower sums. And actually, we can just use this as a diagram, okay? But this one's pretty simple. In terms of our lower sums, there's our lower sums, right? Okay. So our lower sums, we're going to choose those lower values. So in this case, it'll be f of -1/2 times 1, right? Because we're going to pick this one, the -1/2. So that's f of -1/2 is going to be the height for this first rectangle. Then we'll pick f of 0 plus f of 0 times 1. And then we use actually f of 0 twice. So plus f of 0 times 1. And then we've got up here at 1/2. So plus f of 1/2 times 1. Okay. Not 1, 1/2. You're absolutely right. It should be times 0.5 because the interval is 0.5. Okay. So notice this was a mistake, that the interval, it should be 0.5. There's 0.5, 0.5, and 0.5. Because that's the size of the interval. We already evaluated that, 0.5. Okay. So now you can just plug that into your calculation. Okay. This would be 1.25 times 0.5, because you take -1/2, right? It's actually, where we write this, 1 plus -1/2 squared times 0.5 plus 1 plus 0 squared times 0.5 plus 1 plus 0 squared times 0.5 plus 1 plus 1/2 squared times 0.5. And so that then equals well, the reason why we used f of 0 twice is because on the second subinterval, for subinterval 2 right here, the lower sum is at f of 0. And it turns out for the third subinterval, the 0 is also, the f of 0 is also the lower sum for the third one as well. So it happens to be the lower sum for both subintervals. It's shared. right? Because it's the one that's on its left-hand side. Misha asked, why do we include f of 0 twice in our calculation? No, we have 4 intervals. We have 1, 2, 3, 4, okay? No, they just share an end line. So they don't share, like there's nothing shared other than the end line. And this end line happens to be the lowest value for both of the subintervals. So we're going to use f of 0 twice. So this is then going to give me, 6.625 plus 0.5 plus 0.5 plus 0.625, which equals 2.25. So my lower sum is going to end up being 2.25.
Dr. Sweeney?
Yeah.
So you're saying that you basically, for the lower sum, you're using the f at the point that's like the lowest? Like you wouldn't use f at -1 because that one's higher?
Yeah, exactly.
Okay.
Sorry, continue what you were saying.
No. That was my question. I just didn't know how to word it.
Okay. Yeah. So f of -1, right, is going to be bigger. If we actually take a look at f of -1 equals -1 squared plus 1, right? So that equals 1 plus 1. That's equal to 2. So that's a higher place. That's going to make a bigger. That's going to make a bigger rectangle.
So that would be for like the upper sum?
That's it. That's going to be the one for the
Okay.
upper sum. That's right.
Okay, thank you.
You're welcome. So if I look here, right, we actually, let's now take a different color. Let's use red. For my upper sums, okay, so now the upper sum will be in red. We're going to take the highest point. So there's that one there. Then next, there's the upper sum there. It turns out it's also going to be the same for 2 and 3 again, okay? And it turns out, because it's symmetric, it's symmetric about the y-axis. I'm sorry, my picture's not perfect, but you can kind of see that basically those are now going to be our upper sums, okay? And so when I write my upper sum, make this a little bit smaller so I can, there we go. My upper sum is going to be f of now -1 times 0.5 plus f of, in this case, -0.5 times 0.5 plus f of 0.5 times 0.5 plus f of 1 times 0.5, right? So now we're choosing each one of our values there to reflect the upper sums now, okay? And this will then be 2 times 0.5.
You think that's good?
Did you read? It says that they do that to expose it.
But that's how he.
Okay.
So that's 2 times 0.5 plus, and this will be, we already know that this is going to be 0.625 times 0.5 plus 0.625 times point. Oh, wait, no, it's just 0.625, excuse me. So this will just be 0.625 plus 0.625 plus now 2 times 0.5. So that's 1 plus 1 plus 1.25. Okay, so that's now 3.25. Okay, so this is 3.25. And that's just the calculation. What do y'all think? Now, in this case, finding the upper and lower sums was pretty easy because it's symmetric, right? And all we need to do, we're just looking at the endpoints of the intervals. In some cases, you might actually have to go out and find the critical numbers, okay, rather than using just the endpoints. So you might want to actually construct a graph, take a look at the graph, and then use that in order to kind of guide your understanding of where your upper and lower sums are going to be, okay? And again, this is just another method of actually finding the area, okay? On the one hand, you have the biggest overestimate. So the biggest possible overestimate is going to be that upper sum, and the smallest possible estimate, which would be your lower sum. Okay? Any questions on that? Let me actually go over a couple of other things too, because that we're going to see a lot more of. So our delta x, right? This delta x right here, remember, is going to be the end of the interval. So 1 minus -1, okay, divided by the number of intervals. Okay, and so as you're building these, kind of like match up the graph to what this equation's doing, it'll be a lot more intuitive. All right, you're just, the whole idea here is that tells you how big each one of the subintervals is going to be. And then we can see the summation notation right here, right, where we're going to have 1, we always start at 1, and we'll go up to the number of intervals that we actually are looking for, okay? And we'll find some f of x, I, times whatever this delta x is going to be, all right? And so you can kind of see that that's going to be represented in these functions, okay? All right, cool. How are we doing? Good? It's a lot to take in. It's something you want to practice, right? But then it becomes a part of your intuition. And once it becomes a part of your intuition, then it makes doing integrals and a lot more math and a lot more calculus actually a lot easier. And anything that deals with calculus, engineering, whatever. All right, so now let's take a look. Oh, wait, I am in, yep, there I am. I want to go to my next page. Here we go. All right, we got our linear sums. Now we want to talk about distances, right? So basically we've been utilizing this whole idea of physics and working in physics to kind of help us to illustrate calculus. And the truth is that we're not really illustrating calculus. This is calculus. It turns out, I don't know if you guys knew this, but physics is math, right? Okay, like when you do physics, you're basically just going to do mathematics. And in fact, they built the calculus to do physics. Okay, so they can actually do physics. It's really cool. And so hence why all of these things are kind of related. So let's ask this question. How do you calculate the distance of an object if an object is moving at a constant rate? Okay, so we ask this question. It's called uniform motion. And we generally, it's going to be distance equals rate times time. You guys remember that from junior high school, lots of places? The distance is going to equal the rate times the time. Okay, that's our basic function for, well, physics, yes? If velocity is some kind of function of time, right? If velocity changes over time, right? Okay, so the rate is constant. Then what we're gonna have is that the distance traveled is gonna be the velocity times the time, okay? V of t times t. All right, there it is. That's the distance traveled. So what we want to do is we may want to actually go in and we can approximate this distance, right, by dividing the intervals of time into small subintervals, right? So if you imagine, okay, let me draw a little picture of this. You imagine that you've got this thing moving, okay? You've got this piece moving, okay? And, right, or actually, here we go. What I want to do. Yeah. Okay, cool. All right. So if we kind of imagine we've got this object moving, no, that's not how I want to think about it. I want to think about it like, so let's say, for example, right, each one of these represents like a 1 second time block, okay? And the speed, V of t, is based upon how long the piece is, okay? So we have V of t, it's this one right here, okay? We have another one, go a little bit slower. So V of t right here, that's a little bit slower. So that we call this V1 of t, this is like V2 of t. And then we have another one, right, which may be a little bit faster. So that's v3 of t, okay? And then we have another one that goes a little bit faster or a little bit slower called v4 of t, okay? Now, each one of these, right, represents a different velocity at a different time, okay? These happen to be constant velocities, but they're different velocities over the same period of time, right? Each one is like 1 second long, okay? Now, what we get here is we would get, like, if we imagined that we found like this velocity, which was like an average velocity, that average velocity isn't necessarily what's happening at each one of these times, at each one of these time frames, okay? So taking the average velocity over time, right, is not as accurate as taking the smaller pieces of the velocity, right? If we wanted to get a better and better approximate of how far we traveled, we want to figure out how fast am I going in a certain interval, how fast am I going in another interval, right? Okay, for each time, yes, for each like period of time. And that would give us like a better estimate than if we were to go in and just find the average velocity, which is what the r is in the distance equals rate times time. Okay, you kind of have to think about these things a little bit. I don't know if that's the best picture or not. So I go in, and what we're going to do is we're going to kind of represent that as this distance is going to be approximately the velocity function times time, but for a lot of different of these subintervals, okay? These ones here, they're corollary in what we just did, as these are areas of subrectangles, subrectangles. And delta t is like our delta x, and v of t is like our f of x, okay? So this is like our f of x, okay? The area of each subrectangle is going to be the v1 of t times delta t plus the v2 of t times delta t, right? So we're going to take, velocity at each point, right, multiply it by the time in the subinterval, okay? And that gives us our equivalent of an area approximation. And it turns out that this is exactly what's happening, right? That in fact, the distance that gets traveled is going to be the same thing as the area under the curve. It's going to be exactly the same. The area, by the way, under the velocity curve. Okay, so if we want to put that in as a little side note, the area under the velocity curve equals or is the position or distance traveled. Actually, it shouldn't be position. We say it's the distance traveled. And we'll get into the nuts and bolts of that in just a little bit. But it's the distance traveled. Okay? So the area under this velocity curve, we've got the curve of the velocity, right? The area underneath that curve is going to end up being the distance that gets traveled. Okay? Trip out. It's going to be real cool because we're going to use this in order to find position functions. All right. So let's take a look at an example here. Okay? So we've got the speedometer readings for a motorcycle at 12-second intervals are given on this table. So my delta t is going to equal 12 because there are 12-second intervals. All right, 12-second intervals. And now we see the velocity at each time. Okay. So we got at time 0, the motorcycle is going at 30 feet per second. At time 12, the motorcycle is going at 28 feet per second. 25 at 24 feet per second. At 36 seconds, we've got 22 feet per second, and so on and so forth. So these guys, these are the velocities, and these are all the times, and our delta t is going to be just 12, right? You could figure that out, one, just by noticing that the difference between these is 12, or, right, this equals 60 minus 0 divided by 1, 2, 3, 4, 5, 6. Oh, wait. Oh, right, because we're starting at 0. Sorry. Okay. So it should be, yeah, that's fine. We have, it's actually like 60 minus 72. We actually have, these are endpoints. These are endpoints, and they're not actually the number of intervals. We only have five intervals. So it's 60 minus 0 divided by 5, okay? Because here's one interval, here's two intervals, 3 intervals, 4 intervals, 5 intervals. So we have 5 intervals, okay? And 6 endpoints. All right, so let's estimate the distance traveled by the motorcycle during the time period using the velocities at the beginning of the time period, okay? So the beginning of the time period, if we think about that, that's going to end up being, those are like our left endpoints. So we'd start out, our velocity is, we got to have our distance is going to be approximately 30 times 12 plus 28 times 12 plus next interval 25 times 12 plus 22 times 12 plus 24 times 12. So notice I have 1, 2, 3, 4, 5. Okay, 5 of those distance equals rate times times. D equals RTs for each one of them. Okay, so we can do a little quick calculation. And I get the distance traveled is 1,548 feet. Yep. But does everybody understand how we got that? We just took distance equals rate times time. We had our delta t, right? Okay, which we figured out was the size of the intervals between each subinterval. Okay, and then we had the velocity at a specific point of time inside of an interval, right? Like at the beginning in this case. Now let's try it giving another estimate using the velocities at the end of the time periods. So now use the end of the time periods. And I got 1,512 feet. What do you mean, Misha? Misha said, we purposely didn't include 27 times 12 for the beginning of the time period, right? Well, it turns out it's not the beginning of the time period. It's actually the end of a time period. It's not a beginning. So hence you would not be using 27. Just like we would not use the 30 for the ones where they're at the end of the time periods because the 30 is at the beginning. It's at 0. Each time period, right, okay, is represented by the space between 0 to 12, the space between 12 to 24, and not actually the values 0 and 12. It's all the stuff in between, okay? One of the really big challenges of calculus right there is to understand that now we're not as interested in the endpoints, we're interested in all the stuff that's going on in between, okay? We want to know all the things that are going on between, and yeah, there you are. Okay. Any questions on that? It's velocity times time. We end up, it ends up giving us a a very clear sense of the relationship between area under the curve and distance, right? That distance is the area under the velocity curve, okay? Now, are your estimates in parts A and B upper and lower estimates? So what do you guys think? Are they upper and lower estimates? No. Why not, Valet? Valet says no. Why not?
Wouldn't they be left and right?
Okay. Yeah, they're left and right. Okay. That doesn't mean that they're not necessarily left upper and
True,
lower.
but-
Okay. Can we get a reason why? Let's say, for example, why isn't A, okay, an upper estimate? Anybody? You got an idea, Floor? Why isn't A an upper estimate?
Wouldn't it be like a straight line? Because it's constantly moving at the same speed.
It's not constantly moving at the same speed, though.
Um,
If I looked at this graph, right, here's what's happening with this function, okay? Function looks like this. Well, actually, it's kind of hard to say what to the best of my knowledge, my function looks like this. Okay. To the best of my knowledge, this is what my function looks like. All right. We start here. Here's 30. Okay. We'll make this 20. We'll make this 10. Okay. So we go 30 to 28. So here's, and then it says 12, 24, 36, 48, and then 60. Okay. We go 30 to 28, right? And assuming linear progression of the velocity, that's what that looks like. Okay. So that's your first subinterval, goes from 30 to 28. Excuse me. Okay. There you go. Then the next one goes to 25. So right about here. Okay. So that's 25. Now it looks linear, but that's only because I'm not the greatest artist. Well, it's because it's hard to tell. I'm actually pretty good at this kind of stuff, but it's a little hard to tell. So that's the next subinterval. Okay. Then we have 22. Okay. I should have made these all. None of them get down below 20. Should not have used that anywhere else. I should have made it big. Then 24. Okay. Go up a little bit. So there's 24. Okay. And then we have 27. So 27 comes back up to here. Okay. They're not all perfectly linear. They're kind of, but they can kind of get close. So that's our picture. Okay. What is the upper estimate going to look like? If we think about this, we go like, oh, okay. What's the upper estimate going to look like, right? It's going to have, let's do it in red. So there's my upper estimate, right? There's another one. Okay. Here's another one, right? Then here's another one. Yes. And here's this one. Okay. And then we'll use blue for my lower estimate or my lower sum. So my lower sum looks like it's got that one and that one and that one and that one and that one, right? Okay. Are either one of these the left-hand sum or the right-hand sum? Is the blue one the right-hand sum? Take a look. Is the blue one the right-hand sum? Is the red the right-hand sum? Think about it. Let's take a look. Red, to be the right-hand sum, we'd have to start on the right-hand side every single time for the red ones. Do we do that? Are you sure? It changes. That's right. It changes. Take a look. Right, the red one, we start here. That's a right-hand sum. Excuse me, I should make it red. Make it just clear. So this one, that's a right-hand sum. Here's a right. Okay. Here's a, this now is the left. We go back to the right. And we go back to the right. Oh, wait. Yep. Yeah. Right. Got it? Midway, it changes to the left. We look at the blue ones. The blue ones now, we look at this and we go, okay, well, on the blue ones, here's left for the blue. This one here now is, oh, this one actually was left, wasn't it? That was left. This one's right. Okay. This one now is right. Okay. This one here, again, is now going to go to left. And it's kind of tricky now. Got harder. Because we went here, that's the left-hand side. And then here, this one here is also the left-hand side. So it switched for each one. Okay. Yeah, so midway it switches, it's half and half. So the answer is no. My estimates are neither. My estimates in A and B are neither the upper nor the lower estimates. Okay, and that's actually, right, points out another really important thing, okay? You have to consider actually the function that you're looking at in order to determine those upper and lower sums, right? It's not always just the right-hand side or the left-hand side. In the first example that we did with the square root of x, yeah, it was the left-hand side and the right-hand side, okay? But not in this case. All right, okay. So this, for us, finishes up 5.1. Okay, so this is the last of 5.1. And so what you need to do, what you must do tonight, okay, everybody, this does not mean, hey, we've got a, just one section, great, right? What this means is that you've got to go in and you've got to study. You got to do the homework for 5.1 and study for your 3 and 4. I will put up the rubric and the answers for the chapter 4 exam today, okay? And we should have the exam scores in today as well because they're almost finished, all right? Once again, today is the drop deadline. I just like make sure that everybody knows, all right? If you need to email me about that and you haven't done so already, please do so. Yeah. Did you do well on 4? So far, actually, you know what? This is a great point. Let me actually just stop the recording.